So I'm going to start with a little bit of a story. So about 6 years ago, my knowledge of REST, microservices, and all the sort of patterns around it was pretty rudimentary. And we just put a national scale system into place. It was going to millions of people, and it locked up. Well, why? Now, luckily we had Splunk configured, so I managed to do some kind of root cause analysis on the logs, and it turned out that a front-end service was calling a business service, which is calling an integration service, which is talking to a third-party system, which had gone down. An awful lot of these requests came in, each waiting for a response from the external system, and very quickly we just basically became thread starved, everything locked up. So that was kind of a hard fail. And when I say hard fail, it was in the newspapers, so it was pretty egg on face time. And basically we built a kind of distributed monolith. We thought we'd build a nice, robust microservice architecture. We built a distributed monolith. And today I'm going to try and explain how you can avoid some of the mistakes made in the hookahs in my youth a few years ago. In order to do that, what I want to discuss is building microservices using event-driven architectures. Advanced warning, I've stolen a couple of diagrams for this because I didn't have a chance to draw all of them, which leads to kind of a further warning that there are diagrams. I know some people are allergic to them. But before that, I'll say hi, I'm Jeff Watkins. I'm Digital's Chief Engineer. I've got about 22 years in the industry now. And over the last few years, over the last maybe 6 or 7 years, I've started to become more and more interested in services, APIs, REST, and things like GraphQL. And so today, there's a few things I'd like to cover. I'll make my screen move on. I'm not going to read all those out to you, you can read yourselves, but really, one of the key things is like, why would you care? Well, because if you are delivering a system nowadays, really, it's almost certain you are going to be delivering services. As the world becomes more connected, the API economy grows, these things are going to start matching more and more, and people without services aren't going to be able to scale in the cloud, aren't going to be able to leverage the kind of third-party integration that their competitors will be able to. So we're going to first sort of start with really, kind of what a microservice is. Now your mileage may vary in a lot of this. This is kind of a grab bag of concepts and patterns that you may use on sort of case-by-case basis. The example architecture at the end is kind of just there to show how it could all hang together in concert. We have got a very similar architecture we're delivering now for a client. So true microservices. Now people delivering microservices may or may not come as a surprise to you, but really, well, the strength side, it gives you independent deployment. I mean, you can actually take bits of your system in and out of service and deploy them completely independently without any kind of coupling there. We have independent scaling, which means that you can size up and size down services, individual parts of your service ecosystem to meet demands. You don't have to scale your entire estate at once. You can just scale parts of the parts that need to be scaled. It gives you independent data as well, so it keeps all your data stores kind of focused and tight, and stops any individual one from getting overused. Gives you a decoupled and encapsulated design, which means it gives you plenty of reuse opportunities. It gives you the opportunity to match services up in new kinds of interactions that you don't really get in a monolith. It gives you something called shared nothing architecture. It gives you true independence. This means that no libraries, no code is shared between them. This is actually quite a challenge. It allows you also to evolve your design a bit. This means that you can start building up your interactions without having to redeploy or redevelop old ones. It gives you a good idea of single responsibility, and a microservice should do one thing really well. And it allows you to think more of products over projects, because a microservice tends to be around sort of a bounded context in domain-driven design talk or some kind of other concept. They tend to be product-focused rather than projects, which is also good for reuse. They bring some pain. If you're doing a lot of different microservice calls, you are just going to see more call times. It's going to get longer. And breaking up your estate into lots of different parts is just going to make it slightly more operationally complex. This means that you can sort of lean more on your platform provision, your DevOps engineers and your cloud architects to make sure that this estate is working properly. But we're seeing a generalized movement towards that anyway, and putting more things like infrastructure as code in, building more operational complexity to make more software simplicity. It gives you increased design complexity when it comes to designing your flows. In a monolithic architecture, you can just put everything in one service pretty much and just have at it. If you're having to think distributed, well, it starts to get more difficult. And really, microservices, you can't really do distributed transactions with them the way you could with some old style sort of RPC, RMI frameworks. So you have to then think of something else instead. And of course, with the separate data stores means that actually you have eventual consistency rather than immediate consistency. You effectively bin off most of the ideas around asset transactions. And if you've got lots of data, if you're something like Facebook or you're LinkedIn, and this is why Facebook and LinkedIn have both created big data handling solutions. Actually, the number of different reads you could be making to get just a simple page worth of information could be a lot. I was involved in a solution once where they accidentally wrote in 180,000 REST calls to get the reference data on client startup, which obviously didn't scale very well. So that's some of the pain points. So let's have a look at some patterns and anti-patterns of microservices. So some of the patterns we'll talk about today, so there's orchestration and choreography. They sound similar, but orchestration is like a true orchestrator. Orchestration has a conductor, in this case we'll call an orchestrator. Whereas choreography is likened to a dance. All the dancers kind of have been taught how to do the moves and they know the routine. So they all kind of move in the space allocated without bumping into each other, without needing a kind of runtime conductor. They're decoupled, but they're synchronized in kind of that choreography. This is the database per service pattern, which we've kind of touched upon already. There is also some people use a shared database pattern as well, or shared cache pattern. Not going to go into that one too much today. There's API composition. Rather than relying on the client to actually make a series of very chatty calls, which can be very expensive, is you use an API composition layer. And this is where things like GraphQL come in really handy. This CQRS, which is Command Query Responsibility Segregation, it's basically an attempt to get around some of the limitations of the kind of CRUD nature of REST and some of the issues of the API composition pattern. It gives you a clear segregation between the commands you're making, which can kind of turn into events, and your what effectively your reads, your queries. And there's event sourcing, which I'm going to go over. Usually use the CQRS, and we'll go over that in shortly in some detail, and also the Saga Pattern. So let's have a look first at what's as far away from microservices you can get. Well, it's the monolith. We've all seen seen systems like this. Service A, B, and C all exist in the same kind of runtime environment. Means they're not independently deployable or scalable. You have one big old data store. That means the reusability, those services are highly coupled usually. The reusability of that is low to none without you making code changes. It's very project-focused as well. You often find that these are so tightly coupled into sort of project-focused services that if you end up building the same services multiple times across multiple projects, which is a bit of a waste. And the data store, it's a big old data store, one single one, well, it can become very unwieldy. But on the other side, the transactionality is far simpler. Access to data from one service to the other is also very simple because you've got access to the data store. You can maintain referential integrity. You can have foreign key constraints. That's great. It's a simple design, but it's not really very suitable for a modern ecosystem where you've got lots of commoditized services. I mean, for smaller companies or products, actually, this might be perfectly fine. If you go down a really event-driven microservices route, when you're only delivering a very simple service, well, you're probably just wasting your time. So let's have a little look about a distributed monolith. I've already talked a little bit about my own unfortunate case. The thing is about distributed monoliths is they look from a distance a bit like microservices. And that's why people think they're doing microservices, but they're kind of not. So they'll end up with kind of coupled deployments. They'll end up with coupled scaling problems. And the worst case is for having all of your microservices under one runtime environment, which just split it into what look like microservices, which means you're really not much better off than a monolith. The only thing is you might have slightly more reuse. So basically, distributed monolith is a bit of a fail as well. So there's something called mini services, which a lot of people are using as a sort of a band-aid measure. You see on the right here, it's still this one from Gartner, is, you know, the more microservices you get, the more you enable agility. And this is one of the key things here is microservices enable agility of change and delivery, and then without loose coupling. But actually, they're on the other side, obviously, that monolith is much less complex and much easier to operate. So somewhere in the middle is mini services, where you're kind of broken it up a little bit, but it's kind of not much better. It gives you some more options, and you can kind of use the strangler pattern to break bits out bit by bit, which is okay. So one of the other sort of antipatterns is coupled microservices at call time. This is one we see a lot. People write microservices, but then they actually use the REST HTTP calls to call other services. And what happens there is you just end up creating a bunch of synchronous blocking calls that each one has to return, and that timeline gets longer and longer and longer. And eventually, service C goes to sleep for a few seconds, and the entire thing times out. And then you end up with this kind of loss of availability because the client thinks all of it's failed, and actually it's only service C that's failed. But by doing this chaining, you end up kind of failing quite hard. And as soon as you go out onto the HTTP, you're effectively putting yourself in the hands of the network gods, which are kind of unpredictable and capricious, really. So really, in a microservices, an ideal microservice, you want to be doing everything as much as you can in process. And by doing this, you are moving out the process and waiting for a synchronous response. And there's something else which I've seen as well, which is what I call a round-robin death spiral. As if you've got a very chatty service that talks out to another service, maybe does a sort of multicast, maybe it goes and gets 10 or 15 pieces of data from the same service, but it's hitting a different service each time. You see again, the diagram, service B2 is out. Now, if you're just making one call, you have a 1 in 5 chance of failing. Now, if you're making 5 or more calls, you have a 100% chance of failing. So by having this kind of fan-out pattern going through a round-robin load balancer, and by making these calls kind of a synchronous HTTP request, you basically guarantee to fail when one of them goes out, which again is not immediately obvious when you're designing a system, but it comes back and bites you hard. So let's just talk a little bit about data and microservices. So I think the database to service part is the bit that's hard. So having the individual scaling services, especially if you're using something like serverless, like Lambdas, actually the processing, the actual processing is easy. The data is hard. So it's all really easy until you need other data from other services, and you go, well, how do I get that? Or you need to write to another service. You go, oh no, how do you do that without blocking? That's kind of tough. And also, when you get that service, the data from another service, you've lost your referential integrity. So how do you model that? And obviously, if you're updating something, well, you can't really put it in a massive transaction because it's on a different database. And we can't have these distributed transactions putting across multiple HTTP calls. We've already established that directly calling another service is a bad idea. So how do we deal with data? Well, we are kind of going to get to that in a second. Now, one of the first things that people try with microservices is something called the two-phase commit, which is basically a prepare and commit cycle. So you prepare, you sort of get all the data in ready with an open transaction, and this microservice then becomes a kind of a bit stateful because it needs to hold transaction open, which is bad because microservices shouldn't be stateful. And then it does a commit phase. Now, what this doesn't solve is if commit number 1 succeeds and commit number 2 fails for some reason. So it actually doesn't solve the problem. And there's also a third stage, so this is called the cancel stage, or rollback stage. So in microservices term, we call this TCC, which is try, confirm, cancel. So it kind of doesn't really work very well as a pattern. If you've got very simple services, it might work, but it does push more complexities, the service code as well, because you have to do this and you have to keep your services stateful, and you have to have kind of prepare, commit, and rollback stages. So really, it's not a very good option. Two-phase commit's pretty outdated anyway. So there is one sort of atomic requirement for if you're going to do eventing, is that if you've got a service that writes to a database or some kind of data stream, is that you have to write to a database and you have to forward the event into the next chain, unless you're the final thing in the chain. And if the second fails, you have to roll back the database transactions as well. So you're doing all that in process, so you can do that with, the Java and .NET frameworks will kind of wrap this in a kind of transaction. So you can say, right, I want to do a database write and do a write to, say, like a message broker. So you can actually do this. This is kind of the minimum level of atomicity that we need, really, in order to be able to guarantee that we both have durable data and that we also know that we've passed something onto the event chain. It hasn't just kind of fallen into a hole. So let's have a little look about some of the event patterns. So there's orchestrated eventing. This requires you to write an orchestrator. Now this can sometimes be a workflow engine. Now workflow engines tend to be large, cumbersome, slow, difficult to test. But basically you pass the data required into each call or publish an event each time. So it would be set customer data into the order processing service. It can be bulky and there's quite a lot of extra code to write. But what this does do is it gives you kind of a good view on where you are in a process. So service A, service B, service C, and service D do not talk to each other. They don't know about each other. They don't care about each other. If you see it goes 1, 2, 3, 4, 5, 6, and it goes through the call chain, in and out of these services until eventually it gets back to 17 and it's finished. That's the final event. There's quite a lot of events. These can be published on queues or topics. This is an orchestration pattern. This is kind of, some people do this using synchronous HTTP requests as well rather than events. That kind of forces you down kind of a very synchronous locking route, which isn't much better, but it still takes away the coupling between service A, B, C, and D. I would avoid using sort of the HTTP call method for this. And there's choreographed events, which if you look between the two, they look very similar, except there's the orchestrated missing. Now this does kind of require that there is no actual additional orchestration required themselves. So the services can actually deal with the events completely on their own. So it's simpler, it's a smaller, cleaner code base, but you do have no control over the flow in your system. You can change these flows as much as you want, but because there's no orchestrator, there's no actual kind of coherent predefined flow. So this might mean that potentially you could do some weird stuff and it might be difficult to spot that you've done something weird. But neither of these patterns do a really good job with unhappy path scenarios. So is there a pattern that can help us? Well, yes, there is. The Saga pattern. It was created in 1987, so it's not a new pattern. It's basically it's a pattern that's now used as a microservices architectural pattern to implement a transaction that spans multiple services. And what we do is we chain our events into something we call sagas. Now you can either go an orchestration model or a choreographed model for this. But what they do, there's the extra bit on top, aside from the fact that you actually kind of align your events to your event streams to sagas, is you have what we call compensating transactions. So each saga needs a kind of a cancel saga mechanism, and I'll show an example of this in a minute. So this basically allows you to effectively have what is the equivalent of rollback but isn't. So the advantages is, well, it helps maintain consistency across multiple platforms without coupling. Brilliant. However, because you have to code in the compensating transactions, well, it does actually add some complexity over just having a couple set of services. So distributed Saga guarantees, it has two guarantee outcomes: either all the requests in the Saga are successfully completed, or a subset of the requests and their compensating requests are executed, i.e. you cancel the Saga. So these have to obey those kind of characteristics. Now, that also means that the cancel Saga cannot fail. This means it has to be what's called idempotent, which means that if it doesn't work straight away, you need to be able to reapply it until it does work. And it also needs to be commutative, which means that because in an eventing system, stuff can arrive out of order, if you get a cancel Saga request, you cancel, say, a hotel booking, and then the actual hotel booking comes in, you shouldn't end up with a booked hotel. You should end up with a cancelled hotel booking. So it should be commutative, which is a sort of mathematical term, meaning that the outcome should be the same no matter which order you put the operators in. So here's a choreographed version of compensating transactions. You see service A here, well, it does it right, and then what it does is it says, I'm done. And then it goes into B, B says, oh, well, I've got done A, and he goes, right, do it. Now, what it can do there is, if service B fails, it can cancel Saga, and service A will get the cancel Saga notification and write a compensating transaction. And the same thing can happen with C. C can say cancel Saga, and B and A both get that, and they both write their compensating transaction. Now, compensating transaction is like a double entry bookkeeping system. It's not like rolling back a transaction in a database where that transaction never happens at all. So imagine if I take £10 out of your account, but then find out I can't put it into my account. Instead of rolling that back, I would just put £10 into your account. It's kind of like a two-way ledger. So what we can do is that, or we can use something like AWS step functions. So this is actually the AWS step function designer. And what we can do is we can use, so the AWS step function platform is basically chaining together a series of events, including all of the compensating events to the compensating transactions as an orchestrator. And what we call that a Saga event coordinator, basically. So you can use something like AWS step functions to do this. So when you're actually doing all this moving these events around, well, you've got two choices nowadays. Where you can use a message broker, so that if you're on AWS, something like SQS, which is a simple queuing service, or SMS, a simple notification service. So SNS deals with topics, SQS deals with queues. Or you can use data streaming, something like Kafka, or Amazon's AWS Kinesis, which is kind of a copy of a very similar system to Kafka. Now, message brokers are very fast. They can support huge throughput of numbers of messages. They support multiple notification types. You can ping stuff on emails, on queues, on HTTP. Data streaming solutions just tends to go into the data store, which you then have to either siphon out or use a querying system to get it out there. But message brokers are just really not very suitable for large data payloads. If you're bussing around lots of data, things like SQS and SNS will start to creak. But data streaming is slower. It kind of has a kind of a latency period because it writes everything durably to disk first. It's kind of hard to access, but it has these kind of benefits. You can pretty much put any kind of amount of data through it. And also, we can use something like Kafka or Kinesis as an event store. So now, Kinesis as a choice is much simpler than Kafka. It's operationally simple, but it's not as performant. It can't, and you're also limited by how much throughput you can put through it in a 7-day period as well. If you're talking about sort of small to medium sized enterprise, then actually Kinesis probably do for you. If you're talking about if you're something the size of maybe BP, you'll probably want to move to the Kafka route, which has more setup time. It's more difficult to configure. So CQRS and event sourcing. So traditionally, we store data as kind of entities, as flat entities. Now, CQRS and event sourcing can be used together to effectively store a stream of change events for your data in your system. And what you do then is you take those state change events and you kind of rehydrate them together. You take those event changes and stack them on top of each other, and if you take all of the events for say a given order, then that represents the latest state of that order. And what this allows you to do, it gives you like 100% reliable audit log. It's write forward only. You can't delete anything out of it. It persists events, which are kind of a bit more flexible rather than domain objects. You lose a lot of the object relational mapping problems. You can go back and query events. You can go back and replay events. So it's really good for testing and for reproducing bugs. It's more complicated. There's probably slightly more data involved. It's also slightly unfamiliar style program with some people. Now Kafka and Kinesis can actually use CQRS and event sourcing very well, and this actually kind of then merges both your need for an event boss effectively and for an event store together. So this is so a lot of organizations are moving towards event sourcing because of this idea of having an immutable event store. However, so there are some challenges that we need to sort of look at if we're creating an eventing system. Well, One of them is the fact that if you've got a choreographed system, well, good luck in figuring out where you are in any kind of given flow. You can change the flow, you can basically wire them to do whatever you want, but to figure out exactly what's going on in your system can be quite difficult. This is why you might actually want to use orchestration if you want a better idea of what the heck's going on. Workflow systems are actually quite good at tracking state of orders and things like that. You can use things like Splunk and Elk to do distributed logging. If you use correlation IDs and timestamps, you can usually patch together what's going on the system. Or you can use a consolidated event store. If you stream all of your events out as kind of an ephemeral event store to figure out what's going on, you can actually then kind of take a view on that. The other thing is if you're reading data, it can be quite time consuming to take an event stream for an object, say an order or customer, and fold it together to actually form the latest thing. So we use event folding services to actually read a topic partition, i.e. sort of an entity type, be that order, customer, booking, etc. And what you do is you kind of fold them into a local data store. You can do that written to disk. So if you do that on Kafka, you can use RocksDB, or you can do it in memory, which is really kind of limits you a little bit because first of all, there's only a limited amount of memory. Secondly, if you're doing serverless actions, that's really not going to work for you. So it kind of precludes you using Lambdas. Good thing is if your folded event store dies, you just rebuild it. You just go back to event 0 and rebuild it, which is a very handy. That's kind of built into these to Kafka and Kinesis. Now reads, so if you've got lots of microservices, reads, decoupled, everything is on data, so well actually you've got lots of heterogeneous data, it can become complicated, you need to make multiple calls, you need to write an aggregator. REST isn't really suited for that, you can kind of write summary views and bend the model a bit, but the alternative is to make a client spam the service endpoints 180,000 times to gather data, which is slow, too chatty, too network latency ridden. And a lot of data gets thrown away in REST. If you're doing full representation state transfer, you throw a lot of data away. So something like GraphQL can really help us with that because it allows us to retrieve just what's needed when gathering data. So I'm digitally seeing loads of recent projects leveraging GraphQL to make reads a lot easier. Now, for one of our new projects, we're using something called Hasura. We can see GraphQL requires you to write endpoints, to write resolvers, which needs more code. It's not just a bolt onto your database. Where Hasura actually provides this kind of automatically created GraphQL resolvers on top of a Postgres database, and we use this really successfully. And we use Kafka and KSQL to take the data out of Kafka and effectively denormalize it into Postgres, and then use Hasura to automatically expose it using GraphQL, which is super elegant. We've written almost no code to actually do that. It's just config. So all the other things is actually we've now got fully decoupled services. We're using an event store and data streaming. We can harness some AWS except Lambda or Azure functions using JavaScript and the Node.js runtime. I mean, it allows you to pay as you go. It might be more expensive if you've got a lot of calls, but it gives you infinite scaling basically. You don't have to worry too much about building and kind of installing or configuring servers because it's all just effectively just Node.js code. What we can do also is you can use these serverless plugins, things like for the data streaming for Hasura, for Kinesis and Kafka, into Postgres, you can use GraphQL and Hasura on serverless as well. So actually you can use all of these on serverless, not limited by that. So here's a sort of an example architecture. So here we go, we've got clients talking through Amazon AWS API Gateway. So it doesn't know that we're using eventing. So we make a read operation, and that goes via GraphQL into Azure, which looks at the Postgres SQL flattened version of the Kinesis. So in this case, I'm using Kinesis for simplicity. And I've got a bunch of services here that effectively both publish and subscribe to events. They have a local store for event folding, and it's all done as serverless as possible. We've got got a few small local data stores, and we've got Kinesis instance. So this is architectural pattern is very similar to one being used by a current client. They're using Kafka. I put Kinesis in to show that actually you can put a lower bar of entry. If it meets your scaling performance needs, this is a really simple serverless version of the Saga pattern. It'll give you near infinite scaling at the Lambda level, and you can pay as you go. You can use containerized services to save on costs, but that's just going to make it more complicated. You can use Kafka and SSQS if you wanted to as alternatives. I mean, there are a lot of other options available as well. Things like AWS Event Bridge if you need to look at more legacy integration. But really, I think it's time to think about some conclusions. Really, I think there's 3 takeaway pros and cons come out from this as well. Saga pattern-based event sourcing is an optimal side step. We're definitely on our path to it. Projects are moving towards this, especially in sort of modern forward-thinking companies. Kafka and Kinesis are like great solid backbones for providing this event store and actual event-driven behaviour. And using these cloud-native native services really kind of lowers that entry bar, especially if we're working with serverless Lambdas or Azure functions. And things like we can leverage REST, we can leverage CQRS, we can leverage GraphQL, and they can kind of coexist. We don't have to just choose one. But we need to start thinking about distributed systems and more. I think more in the terms of CAP theorem rather than asset compliance. Transactions and rollbacks are kind of replaced with orchestration and coordination and compensation transactions. Your window into process flows means it's kind of going to become a little bit more opaque. You need to put more effort into your design. You can't just kind of slap things together in a kind of imperative way. The imperative flow is really kind of one of yesterday. The kind of free lunch of just imperative systems getting faster and faster is over. We have to start thinking distributed now. And because we're using slightly more architectural components and more cloud components, where we have more operational complexity and possibly a little bit more cost just due to the additional heft of some of these, and also things like the additional storage required by event sourcing and event folding and things like creating read replicas. And I think that's really it for today.